Okay, let's do a very basic introduction to spherical coordinates. Spherical coordinates are 3D coordinates, but instead of having three distances, x, y, and z, we're going to have one distance and two angles. That's called phi, that's called theta. What we want to be able to do is just look at the picture that we normally graph points with and start deriving lots and lots of relationships. So what I'm going to do is just put a little point out here. And of course that doesn't look like anything. We actually have to draw something else so we can see it. So what I'm going to do is drop a perpendicular down to the xy plane, and then we're going to draw actually r in the xy plane. Now r is technically not part of spherical coordinates, but it actually shows up in a lot of the calculations. So remembering that this is a right angle, I'm going to go all the way over here like this, right? And both of these are actually right angles. This just looks like a piece of paper that's actually sitting out. Now, what do we want? We want to draw the distance rho. And so you can see there is rho. Now what is phi? Phi is actually the angle that the ray to our point xyz makes with the positive z-axis. So if you can imagine that theta, we rotate from the positive x-axis. Phi is very similar. It just rotates from the positive z-axis. So the further down that ray goes, the bigger phi gets. What we want to be able to do is just get a lot of relationships now before we actually start doing anything with this. So let's see here. This is r. This is a rectangle, so that's also r. This is z like this. This is also z like this. Now, the distance rho is really just the distance from the origin to the point xyz. So right away we can write down that rho squared equals x squared plus y squared plus z squared without breaking too much of a sweat. I would like to have a relationship with phi and something. You can see from this that I have a right triangle right here. And what I can see is that the cosine of phi is actually going to be the adjacent, which is z, divided by rho. So let me write that down here because I don't want to write it as my final relationship. The cosine of phi is going to be z over rho. So we're going to get that z is equal to rho cosine phi. Similarly, we can see that the sine of phi is going to be the opposite, which is r over rho like that. So we're going to get that r is equal to rho sine phi. Like I say, r is not technically part of spherical coordinates, but it shows up in a lot of the calculations, and its formula is just as important as the others. We'll see why in just a second. So I'm going to write down that r is equal to rho sine phi. Now, I'm going to need this little workspace here. Now, what is theta? Well, strangely enough, theta is the same theta that we actually saw before. So if you're at a point and you want to know what the theta is going to be for that point, you just project down to the xy plane to this point right here, and then just measure theta over. So for example, we're going to see, because x comes straight down, that x is equal to r cosine theta, just as it was before. But r is not part of spherical coordinates, but we now know that r is rho sine phi. So what we get is that x is going to be rho sine phi cosine theta. And similarly, we know that y is equal to r sine phi, but r is equal to rho sine phi, so this is going to be equal to rho, and then sine phi, that comes from the r part, and then sine theta. All the other things we're going to be doing with theta and r will always have the picture, and so I'm not going to write down too much else. I think I may have put more in the conclusions, but we really need to know the picture and use the picture like crazy. So I'm going to stop right here, and just in terms of a basic introduction between the two coordinate systems and the translation picture, we're going to be using like crazy.